Okay, welcome last day. Then not bad. All right. So we're gonna finish up the last chapter since we got one day. Why not? So we'll do it together, and that'll be it, right? A little Thanksgiving and then a little final. Then it's all over in a few days. That's good. That's a good thing. Hopefully, I would imagine. So last time we talked about chapter 16, which was proteins. And a reminder that you do need to know the general structure of an amino acid. So again, that basically is a carbon that has, you know, a carboxylic acid sort of part that doesn't have the hydrogen on it in its ionized form. It also has an amine type of part in its ionized form there in NH3. And remember that that is what is referred to as the Zitteron ion, this sort of ionized version of this. The non-ionized version of it is a completed carboxylic acid on the right and an NH2 on the left, and so forth. And that's what they all share in common. And again, this is oftentimes abbreviated as just COO minus is kind of the shorthand for that in terms of its abbreviation. Thank you very much. And what makes them different is what is sometimes referred to as R, and that is the side group, right? So as we talked about in general, you need to know the general structure. You do need to be able to perhaps classify the amino acids by those sort of four categories we talked about: polar, nonpolar, acidic, or basic. Um, then we talked about really the peptide bond that forms, and when we do get basically two amino acids together, I'll just back it up this way, I guess. We'll just take a look at the end parts here. So this is one amino acid over here. Obviously, it has the rest of the amino acid there. When it comes together, again, we do take out water, right? And the removal of water makes that a mid bond that we saw in organic chemistry. And that is the peptide bond, which puts it together through here. And this is, again, basically the peptide bond, which is, again, the exact same a mid bond that we saw in organic chemistry that puts them together. And that's basically how you put all these sort of amino acids together. And that is what is sometimes referred to as primary structure of a protein is the amino acid sequence. As we talked about, basically, if there are some changes in that sequence of amino acids, it will code for different sort of proteins along the way. We also talked about secondary structure as well, which we had alpha helix. And alpha helix, right, is hydrogen bonding that's occurring every sort of four amino acids down the road. And the result of that, because it's down the road, it will start to give you that coil or helix type of shape as they are sort of hydrogen bonding again down the road from each other. And that is different than beta pleated sheets, where we get the hydrogen bonding actually occurring sort of side by side here. We get the hydrogen bonding occurring. And again, it gives you that kind of folded paper sort of structure as well. Um, Before we move on to the last chapter, there's one more sort of structure of proteins I just want to kind of point out. And that is a picture like this. This is sometimes referred to as the tertiary structure of a protein. And this is within a polypeptide chain of all the amino acids, which obviously here in this sort of line version is the backbone. So that's all the peptide bonding happening, through here. When certain amino acids get near each other, they're able to sort of interact with each other and create this tertiary structure where it kind of folds up on itself a little bit. And that's kind of the folding of an amino acid chain. And there's four different types of interactions that could kind of occur when different types of amino acids get near each other. We could have what's sometimes referred to as a salt bridge or an ionic sort of interaction. And that is your basic ionic interaction, positive side of one amino acid sort of interacting with the negative side of another. In this case, the positive side of the NH3 plus and the negative side of the carboxylic acid. Again, kind of doing positive negative attraction sort of happening. We also talked about this sort of interaction that could kind of affect the overall sort of structure of that protein, and that is again a disulfide bond or linkage. That happens again with our amino acid cysteine, which has, as we talked about, really that thiol group that is present. So again, these guys could come together. We take out the hydrogens, and that's going to link that amino acid together, making that disulfide bond. We also have, obviously, as we talked about, some nonpolar amino acids, and nonpolar amino acids basically have side groups that are obviously mainly carbons and hydrogens. And when those guys come together, we get what are referred to as hydrophobic interactions. That means does not like water. And that's kind of your dispersion forces that we've talked about in terms of intermolecular forces. So we could have some interaction between amino acids by that kind of nonpolar side chains that would come together using really dispersion forces. That's going to kind of hold those together. And then obviously we have some hydrogen bonding that could occur. So we've seen a number of amino acids that have some side chains that obviously have OH groups in them, which obviously has the ability to hydrogen bond. And obviously even some of those guys that obviously has the nitrogen attached to the hydrogen can participate in hydrogen bonding. So these are the four types of interactions that can occur in what is referred to as the tertiary structure of a protein. Again, that's sort of our amino acid, our polypeptide chain all together kind of folding in on each other as a result of the different types of interactions that occur when these parts of these amino acids sort of come in contact with each other. Here's another sort of picture of that. And again, it's basically the same thing we just saw on that previous slide. But we do have some different sort of things happening here. This is our secondary structure. That's our pleated sheets. We have our alpha helix happening over here, again, as a result of that hydrogen bonding occurring down the road. And then now we've got some of those interactions we just talked about. Again, some hydrogen bonding between some amino acids that come in near each other, some of those dispersion forces, more hydrogen bonding, and so forth along the way. So tertiary structure is really taking into account how really the chain will kind of fold up on itself and all those sort of interactions that occur. They're really the same sort of interactions we've been talking about. It's just based on what amino acids get near each other and what interactions you could possibly occur. Any questions on that there? Okay. That wraps up that for good. All right. Let's get rid of that. Okay, so the very last one of the season here, go backwards and talk about lipids. So we talked about carbohydrates, some bread. Yeah, we talked about proteins. Now we're going to talk about lipids. So we're going to talk about fats here. So let's take a look. So lipids are biomolecules. They contain a couple of different parts to them, and we're going to kind of go through the different parts of lipids. They contain either sort of fatty acids or they'll have sort of a steroid nucleus, which we'll take a look at a little bit later on in this chapter. They are soluble in organic solvents, but not water. And as we'll see, they're mainly made up of pretty long chains of carbons and hydrogens. So they have a very big non-polar part of it, which obviously is going to not work really well with water, which obviously will do hydrogen bonding. They're named basically meaning fat. They're extracted from cells using organic solvents, as they would be related to those really big parts of it. Some types of lipids that contain fatty acids are waxes, fats and oils like triacylglycerols, glycerophospholipids, prostaglandins, and steroids, which again doesn't really contain a fatty acid as part of it, has more of that steroid nucleus that we will see. This is a nice little slide, and you should have in your book, but we're going to go through each of these individually. But ultimately, you will be sort of responsible for sort of the components of some of these things. And like I said, we'll kind of go through each of them individually and bigger pictures of what's on the slide, but we'll see it as we go through it. All right, so let's start with what fatty acids are. So fatty acids are really long chain carboxylic acids. So they essentially have a super long chain of just carbons and hydrogens. And at the end, they typically have your carboxylic acid sort of group at the very end. They could have between typically 12 to 18 carbons. They are definitely insoluble in water. And again, that's because even though they may have this polar part over here, they just got a super long non-polar part of it, which is back here. So they've got this kind of non-polar part and it has this polar part. But because of this part's really big, it's not going to allow it to interact well with water, as we talked about, and as we saw with organic chemistry, as the number of sort of carbons and hydrogens increase, the solubility starts to decrease with water. They can be saturated or unsaturated, and that means the same thing as we talked about in organic chemistry. If they are saturated, remember that means that they have the maximum number of hydrogens. Basically, they have no double bonds or triple bonds, they're all single bonded, right? So that's the only way you can have the maximum number of hydrogens per carbon. And what we're talking about, obviously, is this part of the molecule here, where it's all carbons and hydrogens, so they're all single bonded through there. They could also be unsaturated, and just like in organic chemistry, means the same thing. They can, as you could kind of see maybe on this one, they could also have a double bond or multiple double bonds in there, which actually, as we will talk about here, really does affect sort of the characteristics of those fatty acids, whether or not it has sort of double bonds or no double bonds there. So saturated, no double bonds. Unsaturated, it's got at least one double bond in there. Now, the formulas of fatty acids can be written pretty much like organic chemistry. So you could write it in more of a condensed sort of formula. And as to like an earlier question when we were talking about an organic, this is really a lot of times a situation where you'll see that kind of abbreviation where we have the repeatable pattern of carbons because it's usually 12 to 18 of them. People don't want to kind of write them all out. And you got that kind of repeatable one. So remember, though, when you do see a formula like this and maybe you need to count up how many carbons you got going on, you don't want to miss carbons. So that is one carbon in this guy. That is two carbons, but there's actually six of these units have repeated. So that's really six more carbons plus one more there. So this guy actually has eight carbons, one here, six more here from the repeating units of CH2, 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 six times, and one more there, which gives us our eight carbons. So sometimes people quickly look at it and go, oh, it's only got like three carbons, and they forget that that's a repeatable sort of unit. So again, when we see that CH2 with the six, it's basically six of these guys all in a row, and again, hence why they shorthand it there. So you don't have to write them out. So you don't want to miss any of those sort of carbons. We could also write it straight out as we see here. And of course, very commonly, probably a lot of times they are going to be written more in a line structure, just cleaner looking and obviously a little bit easier to kind of draw it out. Remember, just like an organic, obviously everywhere here is a carbon, right? So these are all carbons all the way through there to the end. Now, saturated fatty acids, as I mentioned before, they all have carbon-carbon single bonds, and that's why they're known as being saturated. They basically have the maximum number of hydrogens that you could have. One of the sort of benefits, I guess, or one of the characteristics of a saturated fatty acid is because they are all single bonded, when you get a bunch of them together, they actually fit together pretty well with each other. So they're like all kind of straight. They get to fit nicely with each other. And what that's going to do is remember that since that part of the molecule is really going to be using dispersion forces, which is that non-polar interaction, that kind of temporary weak interaction, the strength of dispersion forces increases with molecular mass or size. So because those are really long, they're all single bonded, they all fit nicely with each other. They actually get a pretty good attraction between those different fatty acids on that part of the chain. They're able to use their dispersion forces fairly well here. And because of that, when we have saturated fatty acids, we get that really strong attraction, and that results in things that have a higher melting point. And typically, this type of fat is more of a solid at room temperature, hence the steak over there, right? So, you got kind of the fatty part of the steak there. And again, because that's saturated, we're going to get a more solid fat as a result of those really tight sort of interactions that's going to occur, even though it's still dispersion forces. It's going to be a strong version of that. Here are a table from your book as well of some different sort of fatty acids. These are all saturated, as you can see. They also all have, long chains of carbons, 10 through 20, and some different places where you find it, like coconut, nutmeg, and so forth. One of the ways we sometimes refer to a fatty acid is by the number of carbons it has and how many double bonds it has. So, for example, this one would be referred to as a 10 to 0 fatty acid. 10 is basically how many carbons, and 0 is how many double bonds. Yeah. Like if we come down here to this guy, this would be referred to an 18 to 0 fatty acid. It's got 18 carbons and 0 double bonds. So sometimes you'll hear a fatty acid being referred to by kind of two numbers. And again, the first number represents how many carbons. The second number represents how many double bonds there are in that particular fatty acid. Obviously, these all have no double bonds, so these are all going to zero out on that second number. When we start getting double bonds, you'll actually have a number that's in there. So let's talk about what happens when we do have some double bonds. These are going to be unsaturated fatty acids. They do contain one or more carbon-carbon double bonds. Typically, they contain a cis double bond, but you could also have a trans double bond. And just like in organic chemistry, right, when we were talking about our double bond, we could have cis, which means the same side of the double bond, or we could have trans, which is obviously opposite sides of the double bond. So here we do see our cis double bond. And again, we have our groups on the same side. Large groups are the hydrogens are on the same side of the double bond. Here's our trans, which are on opposite sides of the double bond. Now, one of the sort of effects of actually having a double bond in an unsaturated fatty acid is, as you can see, especially with this one, that side chain there, or that long carbon chain, is no longer pretty much nice and neat and organized and straight across. You actually get some kinking that occurs in the carbon hydrogen double bond or carbon hydrogen chain. And that does create some issues for unsaturated fatty acids. Because of that kinking that occurs, they no longer will basically sit really nice and close to each other and tight to each other. And what ends up happening, as you can see here, when you start putting a bunch of these fatty acids that have double bonds in them, you get a bunch of kinking that's occurring on these chains, and there's not as close association as you see in a saturated fatty acid. The result of that is they cannot pack together really tightly as you can in a saturated fatty acid. And the result of that is these type of fats typically have low melting points, and they're typically liquids at room temperature because of the double bond that's there that creates, again, just not a good way for those chains to sit nicely with one another. So these are going to be more like your oils rather than like, the solid fat you have on your steak, maybe the olive oil you cook something else with in it. And here again is another table, some unsaturated fatty acids. As you can see, we got butter, we have olives. These all have some double bonds in there. And you can see it doesn't necessarily have to have one double bond, but it could have multiple double bonds, as this one does as well in something like corn. And just like we did with the other ones, we could also classify these based on the number of carbons and double bonds. This would be a 16-to-1 fatty acid. Again, 16 carbons and one double bond. This would be an 18-to-1 fatty acid. Down here we have 18. I'm just going to trust your counting there, but we're going to go 18-to-3 fatty acid. Again, it's got three double bonds in there. Just like you might imagine, the more double bonds you have on that chain, the more kinking that's going to occur. And the result of that is it is definitely not going to sit really nicely with each other. And that's what you see here. If you look at, for example, the melting point, the one with only one double bond has a melting point of 0. The one with one double bond has a melting point of 13. Now down here we got kind of a 18-to-2, 3, and even a 20-to-1, 2, 3, 4. You can see a dramatic dropping of the melting point and all those things, again, because they are not able to be really tight to one another. So we do see a really drop in the melting point. So as you add more double bonds, you're going to affect things like the melting point. You're going to actually lower it because you're not going to get that really tight interaction that you see with a saturated fatty acid. And again, if you compare it to something that has no double bonds, and again, you can see this is like our 12-to-0 or 14-to-0. Here's our 18-to-3. Our guy with 12 carbons and no double bonds has a melting point of 43. Our guy with 18 carbons and no double bonds, 69. But down here, 18 carbons and three double bonds, we're down to minus 17. So a dramatic drop in that as a result of the kinking of that carbon-hydrogen chain. All right, so take a moment here for each of these. Which one would most likely have those melting points? 0, saturated meaning obviously it has no double bonds. One double bond would be an 18-to-1 since it has 18 carbons, and two double bonds would be an 18-to-2. So definitely the saturated one is going to have the chain there that's going to fit really nicely to each other, and that's going to result in the higher melting point. So I would go probably 69 on that one. Obviously here, the one with the most double bonds is going to have a lot more kinking of that chain, which is not going to allow it to sit pretty nicely with each other and have less of an interaction. That should probably end up with your lowest melting point. And then obviously our guy here in the middle should fall somewhere there in between. Any questions on that there? All right. Let's talk a little bit about prostaglandins. Prostaglandins have 20 carbon atoms in their fatty acid chain. They have an OH group at carbon 11 and 15. And they do have a trans double bond at carbon 13 there. And prostaglandins are produced as a result of injury to your tissue. That looks like a hammer to a thumb. Probably is going to hurt. It's involved in pain, fever, and inflammation. But it's not produced when you use some type of anti-inflammatory drug such as aspirin. It inhibits is synthesis. I'll spit that out. So you hit your thumb there, you're going to start producing this. You take some pain medicine there, and it hopefully will stop, obviously, the formation of those guys, and hopefully stop some of your pain and inflammation, and perhaps fever. Unless you pick up the hammer again and miss again, I suppose, right? All right, let's talk a little bit about omega-6 and omega-3 fatty acids. Fatty acids are typically omega-6 when we find them in vegetable oils. And what does omega-6 mean? It means it basically has its first double bond at carbon number 6. Now, kind of different than how we count things sort of in organic chemistry, especially when we're doing kind of omega-6 and omega-3, is normally when we look at this, we really start counting sort of at this end where this carbon would be. In this case, we're actually going to start counting on the opposite side. So the opposite side of it for the omega-6 and omega-3 fatty acids. So if we come here, we're going to actually start counting here, and that's one carbon. Remember, there's four of them in here. So that is five carbons. And right here at carbon number 6, that is where we see our double bond happening. So again, a little bit different than organic, where we normally kind of start counting from this end. We're actually for omega-3 and omega-6 counting the opposite end along the way. In fish oils, they're commonly omega-3 fatty acids, again, meaning the same thing. On the opposite end of our sort of functional group there, we can start counting one carbon, two carbons, and right there is going to be our three carbons, and that's going to give us our omega-3 fatty acids. Linoleic acid and linolenic acid being our omega-3 and omega-6 previously there, fatty acid. We can see here a couple other examples of it. There's our two there. We also, again, can see if we count this way, we got 1, 2, 3. We also have 1, 2, 3, 4. Whoops. That's 4, 5, and 6 as well. So this one actually has omega-3 and 6, so location of those guys as well. So with the omega-3 and 6, we're counting opposite of where we traditionally count. Opposite side of that is where we start counting. All right. All right, so although you will not have to draw any of these, but again, obviously maybe be able to recognize, obviously we'll take a look here. If we wanted to write a fatty acid that has 10 carbons, that is saturated, it would look something like this. If you did more of a line structure, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And again, we would have our sort of bond on that side there, and saturated would mean that it has no double bonds. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. I counted right. That's not bad. If we had a monounsaturated, which mono obviously means just one double bond, and that's what monounsaturated means, and it's omega-3. We would borrow our same structure here: 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And you can even put the H if you want on that one. So 3 would be 1, 2, and 3. So we would have our double bond happening right about there. And obviously omega-6, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And 6 would be, again, counting opposite side: 1, 2, 3, 4, 5, and 6. We would have a very badly drawn double bond at an angle going in that direction. I'm going to kind of clean it up a little bit there. Let's take a look at theirs. Probably much better picture than I did there. There we go. And again, we do see at carbon 3, carbon 6 is where a double bond starts, and obviously saturated, no double bonds in there. That would obviously be more of the condensed structure that you have there. All right, let's talk a little bit about waxes and other things. Waxes are esters of a saturated fatty acid and a long chain alcohol. That is, again, the same ester bond that we had in organic chemistry, which is basically that bond right there, is sort of our carbon-oxygen double bond to our oxygen to our carbon. And that's what we see right about here. And beeswax, carnauba wax, as you can see, again, is our fatty acid part, which would be kind of from this side. It's our fatty acid part. Over here is our long chain alcohol part on that part of it over here. And same idea here. Obviously, this one has a lot of carbons. That's one carbon there. That's 24 more carbons is 25. 26 carbons happening there on the fatty acid chain. So a really long chain. The alcohol part's not that short either, as you can see. Alcohol part has 1 carbon and 29 more, which is 30 carbons there in that chain. So a pretty long part of that as well. That is also one of the reasons, obviously, if you use wax, it is definitely hydrophobic. It does not like water, right? You wax your car, water tends to bead on it, right? Because again, that is a very non-polar surface that would use dispersion forces. Water obviously wants to use hydrogen bonding, so water tends just to bead, or like on an umbrella, right? It will just kind of bead on it rather than sort of spread out, right? Let's talk a little bit about triacylglycerols. And triacylglycerols are also called, our fats and oils are also called triacylglycerols. They're sometimes referred to as TGs or TAGs. And they are esters of glycerol. They're produced by the same esterification reaction that we saw in organic chemistry. They're formed when the hydroxyl group of glycerol reacts with the fatty acid, carboxylic acid group there. So this is one of the things that you do need to know, the components that make up a triacylglycerol. So triacylglycerol is basically made up of glycerol, which is this guy here. So that's the glycerol unit, and basically 3 fatty acids. So a triacylglycerol basically has 4 structural components. It has a glycerol and 1, 2, and 3 of those fatty acids together, and that all together makes up a triacylglycerol. Once again, we could see kind of our glycerol unit here and our ester bond basically happening. So our esterification reaction here, where we're basically removing water, right? And we are left with that ester bond that comes out. So basically you have that same sort of esterification reaction that we saw when we were doing organic, where we take out the water and then kind of bond everybody together through that ester bond that basically occurs. And here's a better look at it there. And obviously in this case, we actually make 1, 2, and 3 ester bonds in this particular triacylglycerol. Olive oils contain a high percentage of oleic acid, which is a mono unsaturated fatty acid with 1 cis bond. And you can see that is basically our glycerol unit. Here's our fatty acid. And again, you can see as a result of those double bonds, we're not going to get a lot of really close association of those carbon-hydrogen chains. The result of that is olive oil here, right? A more liquid fat rather than obviously a solid fat at room temperature. You don't have to worry about what the fatty acids are here, so you don't have to name any of them, so you don't have to worry about it. So we will not worry about that question there. As we just saw there, a triacylglycerol that is a fat is typically a solid at room temperature. It is prevalent in what we see in meats, whole milk, butter, and cheese. Ones are again more of oil or liquids at room temperature, and obviously we'll have a lot more unsaturation that occurs than obviously in the more solid one, which will be more saturated. So oils with unsaturated fats will have cis double bonds that again cause that kinking. Doesn't allow them to come tightly to each other, and again going to lower that melting point and more liquids at room temperature. Let's talk a little about some of the chemical properties of this. The chemical properties of triacylglycerols are similar to what we see with alkenes and esters. They actually go through similar reactions. They do go through a hydrogenation reaction, and that hydrogenation reaction is the exact same one that we talked about in organic chemistry. Hydrogenation is a fancy way of saying I'm adding H2 basically. And what we should hopefully remember from organic is if we have a double bond and we add hydrogen to it, double bond goes away, becomes a single bond, and we add in the hydrogen, right, to each of the carbons. So this reaction also occurs with triacylglycerols. That is perhaps maybe you've heard of the term partially hydrogenated oils, right? It's a partially hydrogenated is basically that process where you throw hydrogens back onto these guys. And what it does is it goes from a more unsaturated fat to a more saturated fat because you're removing some double bonds. And it goes from a more sort of liquid, if you will, state to a more solid state. Hence the margarine that you might have bought, right? So that's the idea there. They kind of hydrogenate it a little bit, get rid of some of those things. It can also go through hydrolysis. Hydrolysis is basically that adding of water. And just like we talked about with the esters, there's an acid hydrolysis or a base hydrolysis, and that will produce one of two things. If you remember, the base one will produce the saponification, kind of the soap reaction that we kind of talked about when we did it. The acid one will kind of get you back to the original kind of components, the carboxylic acid, and obviously the alcohol that would occur as well. So as I mentioned a second ago, the hydrogenation reaction will convert some of those double bonds in these types of fats into single bonds. The result of that is that side chain or that long carbon hydrogen chain will now sit a little bit better with each other, and it will increase the melting point. And like I said, kind of turning some oil into things like margarine and some soft butter there and things like Crisco as well. And as you may imagine, you essentially just need enough hydrogen to get rid of all the double bonds you have. So in this case, we had one double bond, two double bonds, and three double bonds. And if we add kind of 3 shots of hydrogen there, that's going to turn each of those double bonds into single bonds. And we will end up with something that is more saturated. So definitely in this process, going from a more liquid state with those double bonds where they're not going to sit nicely with each other because of them, to a place here where these guys are going to sit pretty nicely with each other and going to kind of increase the melting point and become a little bit more solid. And since you don't have to worry about names, we're not going to worry about that for sure. Olestra, I don't think it's on the market anymore. That was an old time. Olestra was a artificial fat they used to use in chips. They mainly in chips. They use it in a lot of things, but they were in Wow chips. They were from Lay's, I think. So you could eat a whole bag of chips and not worry about it because you didn't actually digest the fat in your body. It would just go right through you, basically, and you wouldn't digest it. So, what's that? There were some side effects that it wasn't so great for a lot of people with that, I think. So I don't think they're on the market anymore. If you can imagine it's not absorbed in your system, that it might cause you some problems that kind of go right through you, perhaps. So some of the issues. So I don't know if they probably use some form of it in other things, and maybe just don't advertise it like they used to. But that's a lot of years ago. They used to call them Wow chips, and it was made with that sort of artificial fat. But there's some issues with that. I think some people have some issues with that, not everybody. But I think they probably still use it in some things and maybe just call it something different. So cis and trans fatty acids, unsaturated fatty acids, the cis, just like an organic, has kind of the bulky group on the same side. So here you can see the bulky group is the long carbons on each side of that double bond, and the trans is opposite sides there of the double bond. And that also gives us some trans fatty acids. And trans fatty acids are sometimes formed as a result of this hydrogenation reaction. So in the process of starting to remove some of the double bonds, you actually end up converting some of those cis double bonds actually into trans double bonds. And in the body, they do behave like saturated fatty acids. That's probably a little bit older of a number there on this slide, but they used to make up a good percentage of our calories. But a number of years ago, they tried to get rid of a lot of trans fatty acids, as it was found to sort of raise your LDL cholesterol, which is your lousy cholesterol, right? And kind of lower your HDL, which is like your heavenly good stuff, right? So let's say a lot of years ago at this point, they kind of moved away to try and use less trans fatty acids and in the food industry and stuff like that because of some of these factors that occur. All right. So take a moment for each of these, decide true or false here. Fats and vegetable oils, that should be true, right? Unsaturated would have some double bonds and not allow them to sit tightly to each other and be more of a liquid. Vegetable oils have higher melting points than fats. That should be false, right? That's why they are liquids. Hydrogenation of oils converts some cis double bonds to trans. That is true. And animal fats have more saturated fats. Again, that's what allows those chains to sit nicely because there's no double bonds and what gives them that more solid sort of feature. Go. Now, just like we saw sort of in organic chemistry, it can also go through the hydrolysis reaction, which essentially will split it back apart into its original thing. So this is the acid hydrolysis, and here's our H plus, which again indicates that's an acid catalyst and acid hydrolysis. And this is the one where we do get back, as we talked about, really everybody completed. So we do get back really our glycerol, kind of like our alcohol part, if you will. And we do get back our carboxylic acid sort of completed, which is our fatty acid on the right there, and obviously our glycerol unit on the left. So in an acid hydrolysis of a triacylglycerol, you basically get back both of the components of it, in this case, all four components of it in their completed form. Now, in the saphonification reaction, which is really the base hydrolysis of it, this is what we were talking about earlier in organic chemistry when we talked about this reaction. This is really the process that's used to sort of make soap. And the result of that is it's a base hydrolysis, potassium hydroxide there is a strong base. It can also do with sodium hydroxide as well. And in this particular case, when we go to break these guys apart, we are not going to get back sort of our completed unit. We will get back the glycerol unit, but we will essentially make a bunch of soap. And as we talked about, I think during the organic sort of lesson, soap really is just a long chain fatty acid, bunch of carbons that again also has basically two parts to it. Again, it has that non-polar tail and it has the polar head here of it. And as we talked about, that works really well as soap, basically, because again, most dirt is non-polar. And because of that, it is definitely going to be super attracted to the non-polar site here of soap. And again, it will surround my little squiggly lines are the carbons. It will surround the dirt with the non-polar part of soap, and it traps it what's known as a micelle and kind of just traps the dirt in it. And as we talked about as well, what it does is it also sort of aligns its polar part of those soap molecules on the outside. And that works really well. Obviously, as we talked about, once you kind of trap the dirt, you typically wash it off with some water, and that water is going to work really well with the outside of soap because that is basically polar and that's polar. So that's what is sometimes referred to as a hydrophilic part of the molecule, which is water loving and likes water basically. So when it washes it off, it mixes well with the water. The outside part, the inside part that has the dirt trap goes away, and obviously you're clean at that point, hopefully, you know. All right, and again, since you're not responsible for any names or anything like that, you don't have to worry about that, so we're not going to worry about it. And again, here, this is a hydrogenation of this, and since we are adding 3 hydrogens, it's going to take care of each of those double bonds and going to basically just turn them into single bonds. Hydrogen goes to each carbon in it, and we'll end up with, again, those guys now single bonded out. So obviously going from, as we've been talking about, a more unsaturated, lower melting point to a more saturated increase in the melting point in this hydrogenation reaction. All right, the next thing we're going to talk about is glycerophospholipids. And just like the triacylglycerol, you should also know kind of how many components there are in this and what makes it up. So in this particular case, we also have a glycerol unit. We have two fatty acids. We have a phosphate group and an amino alcohol. So a glycerophospholipid, which is the most abundant lipid in cell membranes, is composed of, as you can see here, five sort of structural units. Again, a glycerol, two fatty acids, a phosphate, and an amino alcohol, like choline. So these guys are going to attach to our glycerol in the normal fashion as we just saw. This phosphate and amino alcohol will make a little slightly different connection to it. Now, glycerophospholipids are do contain two non-polar fatty acid chains, a phosphate group, and an amino alcohol. And these are some examples of an amino alcohol, like choline here is an amino alcohol. It's kind of like an amino acid, obviously, with the alcohol part of it over here on that part of it as we look at it. Now, the structure here, as you can see, has basically makes two parts to a glycerophospholipid. There is a non-polar tail, which is our fatty acids. So those are our kind of in yellow there, are two fatty acids. And then there's also this polar part, which is made up of the phosphate group and that amino alcohol. So that works really well for this kind of lipid. It has kind of a polar part and a non-polar part. So again, it can kind of interact with both of those things and kind of prevent certain things from going through and other things being able to sort of interact well with it. So we do have our ester bonds that are happening here, just like we saw in the previous one as well. And as I mentioned before, basically it is five structural components to make this up: two fatty acids, a glycerol, phosphate, and a amino alcohol. Sphingolipids also, you do need to know kind of the parts to this and how many things make it up as well. It's a good one. So it is similar to phospholipids, like we just saw. It contains a sphingosine, which is a long chain amino alcohol. It contains a fatty acid and a phosphate, and also a small amino alcohol as well. So this guy here is similar to glycerol, but slightly different. It has, again, a fatty acid, a phosphate, and an amino alcohol. So this guy here does have four sort of structural components that make it up. It has also a polar and non-polar region. It's the same as what we were just looking at previously. Obviously, here our long fatty acid chain is going to be the non-polar part of it, as it has all those carbons and hydrogen, which is definitely non-polar. And over here we have alcohol and amino alcohol and some phosphate. That's going to be our polar part of this molecule, just like we kind of saw in the previous one there. Sphingosine is a long chain unsaturated amino alcohol. So it has very similar sort of characteristic, if you will, of a glycerol. It's got kind of the three carbons. It's got the couple of OHs, but it does have kind of an amine group there in the middle. And obviously a little bit longer of a carbon chain there up on top rather than just the three carbons that we see in glycerol. So it's similar, but a little bit different than what we see with glycerol, again, because it has obviously a lot more carbons attached to it. And here's an example of this. This sphingolipid is one that's found in the nerve cells. And again, you can kind of see the connection there. It has actually an amide bond between the fatty acid and the sphingosine. So our fatty acid in here is going to make our amide bond. And again, our same bond that we saw in organic, which is our carbon oxygen to basically an amine attaching there. And that is what's happening. Obviously, if you remember on our guy there, that was like on our amine group, and obviously a carboxylic acid from our fatty acid coming together. We have our amino alcohol like choline over here, again, making this our polar part. Obviously, non-polar part here, also non-polar part over here, as well as obviously there's a lot of just carbons and hydrogens that are there. So for this one, again, kind of four structural parts to it. And that's a good thing to know. The steroid nucleus consists of really a bunch of kind of organic guys there. It has three cyclohexane rings, as you can see there, and one cyclopentane ring. It does not have any fatty acids, so this is what is referred to as a steroid nucleus. Um, Obviously, again, no fatty acids, not exactly like all the other sort of lipids that we talk about. This is cholesterol, which obviously is the most abundant steroid in the body. And you have some LDL and HDL happening in your body. It has some methyl groups, an alkyl chain, some OH groups attached. And once again, here you can kind of see its steroid nucleus happening in that case. All right. Out of slides. That must be good, I imagine, right? All right, that wraps up chapter 15.